All right, let's start talking about some properties of random variables. And we'll open up with definition 4.1 here. Let x be a random variable with probability distribution f of x. Probability distribution f of x. The mean or expected value the expected value of the random variable x is defined as such. We use the letter mu, the Greek letter mu, mu. That's what that is. Mu is equal to the expected value of x. So either one, this is just notation. The mean, sometimes we use the letter mu, sometimes we use the expected value of x. I sort of like the expected value of x with the capital E because it kind of looks like in operation, if you will, and it also I get to see we're talking about x. So if there's ever ambiguity on as far as maybe you have a joint distribution or whatever you're talking about, it's nice to see that we have an x so we know what we're being referring to. Anyways, the expected value of x is equal to, it's computed in two similar ways depending on if it's discrete or if it's continuous. If it's discrete, we're just going to sum over all of the x values that it can take on, and we're going to take that x value and just multiply it by the likelihood that occurs, f of x, if discrete. And in the continuous case, we do the same thing, except we are integrating then over all of our possible values, x times f of x dx, if continuous. If continuous. And that is the expected value. That is the mean of your random variable. So, I would like to dive into an example. Let x be the face value of a standard die roll. Roll a standard 6-sided die, face value of a single fair die roll. Okay. Find the mean of x then. Let's find the expected value of x. What's the expected die roll value? Find the mean of x. Let's find the mean of x. Okay. All right. So what I would do here is I would start out by, well, let me just write out the probability distribution for x, right? Because we roll a standard 6-sided die here, 1, 2, 3, 4, a 5, or a 6. Standard die, all outcomes are equally likely, so the probability of getting any of these individual numbers is just 1/6. Now, how do we use our definition to compute the expected value of x? The expected value of x, in this case, we're going to be summing over the 6 values. So x is going to go from 1 to 6 because those are all the possible values that we have to take on. And then we're going to choose, or we're going to take each x value and multiply it by the likelihood that occurs. Now, f of x is always going to be 1/6 in this case, but that's just coincidental. So I'm going to write this out still, just so we can see the pattern. So x takes on the value 1 with probability 1/6. So that's 1 times 1/6. So there's x, and then there's times f of x. And then x takes on the value 2 with probability 1/6. So there's x, and there's f of x. In this case, that would be f of 2, right? That would be f of 2, just happens to be the same. Plus 3 times a 6th, plus 4 times that probability, which is a 6th, plus 5 times that probability, which is a 6th, plus 6 times that probability, which is a 6th, And so we need to run that through a calculator and add everything up. And if we do so, we should get 3.5 exactly. 3.5. And that would be the expected value of a die roll. 3.5. 3.5, that's the mean of our random variable. It does not need to be a value that it can actually take on. The mean of a random variable does not have to be a value that your random variable can take. We cannot roll a 3.5, but that's okay. This is saying this is the expected value. We cannot roll a 3.5. All right. A lot of times when people think of the word expected value, in the discrete case, they think, what's the value that's most likely to occur? That's not really what this is saying. This is more of like an average-ish value, if you will. Okay, so 3.5 is, in fact, the correct response there. Okay. Let's take a look at another example here. Suppose you flip a biased coin. Suppose you flip a biased coin that's 3 times as likely to land heads as tails. That is 3 times as likely to land heads as it is tails. Let's find the expected number of heads if the coin is flipped twice. Find the expected number of heads if the coin is flipped twice. Find the expected number of heads if the coin is flipped twice. All right. So this would be a relatively straightforward exercise if we had a probability distribution like we did above that we had for the previous example. So first, we're going to maybe need to go through and find out what that probability distribution is. So what is the probability of getting a heads? Equal to, and what's the probability of getting a tails? Let's figure this out. Coin that is 3 times as likely to land heads as it is tails. So I would say let's let the probability of getting a tails be P. Then probability of getting a heads, it's 3 times as likely to get heads as it is tails. So if there's a P probability of getting tails, there will be a 3P probability of getting heads. 3 times as likely. All right, so since then the probability of getting a tails plus the probability of getting a heads is equal to 1, that would mean then that P plus 3P has to equal 1. Probability of getting a tails is P, probability of getting heads is 3P. So we can solve this for P, and we see that P is a quarter. So the probability of getting a tails is a quarter, and probability of getting heads then would be 3/4, right? So probability of tails equals a quarter, and the probability of getting heads is 3/4. Okay, and what are we doing here? We're flipping a coin twice. This coin is going to be flipped twice. So let's go ahead and let capital X count the number of heads in 2 flips. Set up my random variable here, number of heads in 2 flips. All right, and we need to figure out what the probability distribution of that is. So what are the values that X could take on? X could take on 0. That would be 0 heads in 2 flips. So we flip it twice. There's only one outcome associated with that. That would be a tails, tails. Tails, tails. So what's probability of getting a tails on the first flip? That's a quarter. And then times tails on a second flip. These flips are independent naturally, so we're going to have a 1/16 chance. Probability of getting 1 heads. Let's be careful here. You could go heads, tails, right? Or you could go tails, heads. And so let's see. Probability of getting a heads first is 3/4, and then tails would be 1/4, plus the probability of getting a tails and then a heads. So tails is 1/4, and then a heads is a 3/4 probability, okay? Cool. Notice these are actually the same products, just in a different order. And because of the commutative property of multiplication, we can actually just do this together, right? This is 2 times the same quantity. This is 2 times 3/4 and 1/4. So that would be 3/8, I believe. Looks good. What's the probability that x is equal to 2? 2 heads and 2 flips. There's only one outcome with that. That is heads and a heads. And so that's going to be 3/4 on the first flip, 3/4 on the second flip. So 3/4 squared is 9/16. 9/16. All right. 9/16. There we go. So we have some important information then. What's the expected value of x? Expected value of x would be the sum. In this case, x goes from 0 to 2, right? X could take on the value 0, 1, or 2. X can go from 0 to 2. X times f of x. So when x is 0, what's the probability it takes on the value 0? That would be 1/16. So this is 0 times 1/16. Right? There's x, and there's my f of x value. Plus 1. X takes on the value 1 with probability 3/8. Right? So when x is 1, what's that probability? That is 3/8. When x is 2, the probability is 9/16. 9/16. All right. There we go. And so we just add everything, do the multiplication, everything together here. 3/8 plus 2 times 9/16. That is 3/8. Also, note the 0 times 1/16. That's just going to 0 out. So we have 3/8 plus 9/8. That is 12/8. Also known as 3/2. Or in terms of the number of heads, that is 1.5 heads. 3/2 or 1.5 heads. That is our expected value. There we go. Awesome. Good. Okay. This logically should make some sense, okay? For 2 reasons. One, the expected value of x should be between the lowest and highest value that your random variable can take on, right? In some sense, right? If we got an expected value that was either negative in this case or larger than 2, there's no way we can expect to get 3 heads, for example, when we're only flipping the coin twice. So at the very least, there's a minimal logic check to say, did we make a glaring, mistake somewhere? Does our answer make some sense, right? Should be between 0 and 2, right? Now, also, I would say in this case, once we found this probability here, that the answer is really intuitive. You flip a coin twice. What's the expected number of heads you get? Well, let me ask you this. Since you know that the probability of getting a heads is 3/4, let me rephrase that. 3/4, aka 3 out of 4. Probability of getting heads is 3 out of 4. If you flipped a coin not twice, but 4 times, how many heads should you expect to get? Well, naturally, if the probability of getting a heads is 3 out of 4, and you flip a coin 4 times, you should expect 3 of those 4 to be heads on average. So if we're going to flip the coin twice, which is half as many flips, we should expect half as many heads. Half of 3/4, 3/2. Just some food for thought there. All right, we did a couple of discrete examples there. Let's do a continuous example before we get too far along here. Let's find the expected value of x when the probability distribution f of x is as follows. It's continuous with 20,000 over x cubed when x is greater than 100 and it is 0 otherwise. 0 otherwise. All right. Let's find the expected value of x here. Okay. The definition of the expected value of x in the continuous case is that you'd integrate over all possible values x times f of x dx. So how do we work with this in the continuous sense? Well, we can update our bounds, at least, because we know that this integral value is going to be 0 for anything that is not above 100. So our lower bound, x is greater than 100, so we should go from 100 on to infinity. X times f of x dx. So you're just going to substitute in f of x. So we have x times, and then what is f of x here? F of x is 20,000 over x cubed dx. And we just do the integral, evaluate our integral here. So we whip out our calculus hat. Let's see what we have. Integrate from 100 to infinity. What is x over x cubed? X over x cubed, we can cancel one of these out, and that's going to leave us with an x squared there. So I have 20,000 divided by x squared. In order to set up the integral, I'm going to write that as 20,000 x to the minus 2 dx. Now we can just apply the power rule here on the integration. So this is going to be 20,000, and then increase our exponent by 1 and divide by our new exponent. Evaluate from 100 to infinity. And so let's work through the plug in your endpoints here. Before I do that, I'm going to rewrite this and absorb the minus sign into the bound. So I've got 20,000. X to the minus 1 is just divided by x. And I absorb the negative into the bounds of integration and flip my bounds, go from infinity to 100 now. And so what do we have here? Plugging in 100, 20,000 divided by x, 100, minus 20,000 divided by infinity. Of course, this is bad notation as far as the calculus goes. Don't let your Calc 2 instructor see you do this. And if it's me, I will yell at you. But if we're in stats right now, we're going to loosely say 20,000 divided by a large number. We know that goes to infinity. So this is 20,000 over 100. 200 is the expected value here. 200 is the expected value. All right. Again, quick logic check just to see if this makes sense. 200 is within our range or our domain here of a random variable. It says that x is anything greater than 100. So 200 is definitely a valid answer there. So it looks good to go. All right, so there's the continuous case. Got to pull out your calculus skills and work with that. All right. That's going to do it for this introductory video. For now, let's take a break. If you have any questions or are looking for clarifications, post those in the discussion thread below. Otherwise, we'll see you in the next video for some more examples.